Chirality and enantiomerism. This is second part of optical isomerism. The molecule which are non-superimposable on their mirror images are chiral compounds. For example, let us take the case of this molecule when its mirror image is formed. It is like this. Now this molecule is not superimposable on this one, and non-superimposable mirror images are known as enantiomers. They are enantiomers and are optical isomers. If one rotates the light in right or clockwise, then other rotate in left. One is D, other is L. One is plus, other is minus. But we can't say that by looking at the structure that it is dextro or levo. That is only predicted by using instrument that is called polarimeter. Polarimeter is used to identify the molecule is dextro-rotatory or levo-rotatory. But this is the condition, and that is means molecule are dissymmetrical. There is dissymmetry is the condition for the molecule to be optically active, and the carbon which is attached to 4 different atoms or groups is known as chiral carbon. The molecule having only one chiral carbon is always optically active, but it is neither necessary nor essential condition for the molecule to be optically active. Even there are some molecules in which there is no chiral center, but that is optically active. Another example, if we have 2 chiral carbons like in tartaric acid. This is tartaric acid. If we draw its mirror image, it is like this. It has plane of symmetry. What is plane of symmetry? The plane which divide the molecule into 2 equal halves. That is called plane of symmetry. This molecule has plane of symmetry. And second, the mirror image is superimposable. Now see, if we keep it like this and put it here, it is non-superimposable. But there are 2 conditions. First, same molecule or after rotating 180 in the same plane. See, if we rotate it at 180 in the same plane, it becomes like this. It becomes identical. So these are superimposable mirror images, and these are not isomers, they are identical, and such compound is known as Mezzo compound. This is a Mezzo compound and this is identical to it. They are identical, and this is only one isomer, and that is called Mezzo compound. The molecule has 2 chiral centers, but it is a chiral molecule. Molecule is optically inactive. It cannot rotate the plane of polarized light. Let us discuss the case of the same molecule, but now HOH and OH. Now there is no plane of symmetry. Now if we draw the picture of its mirror image, OH on the same side, H other side, H, OH. Now this molecule is non-superimposable. Even if we rotate at 180, this remains same. So these are non-superimposable mirror images. Means molecule is dissymmetric, and that is why they are optically active. And such isomers which are non-superimposable mirror images are known as enantiomers. They are known as enantiomers. So 1 and 2 are enantiomers. One rotate to the right and other rotate to the left by equal degrees. One rotate clockwise, then other rotates anti-clockwise. Now its third part, this is Mezzo compound. So what is the relation between 1 and 3 or 2 and 3? You know, 1 and 2 are non-superimposable mirror images, but 1 and 3, there is no mirror image relation between them. That's why they are known as, they are isomers of the same compound, but there is no mirror image relations. That's why they are known as diastereomers. What are they? Diastereomers. 1 and 3 as well as 2 and 3. They are diastereomers. So what are enantiomers and diastereomers? Enantiomers are one which are mirror images. Which type of mirror images? Non-superimposable mirror images. Those are known as enantiomers. Now 1 and 3, there is no mirror image relation, but isomer of the same compound. That's why they are known as diastereomers. Yes, enantiomers are always optically active, but diastereomers may or may not be optically active. Enantiomers have same physical and chemical properties. Diastereomers have different physical properties. The pair of enantiomers, equimer mixture of enantiomer, is known as racemic mixture, and racemic mixture is optically inactive because one rotate to the right, other rotate to the left by equal amount, so net rotation is 0. But Mezzo compound is also optically inactive, but in this case one part of the molecule rotate the plane of the polarized light to the right and other part rotate to the left. It is optically inactive because of internal compensation. They are internally compensating, but this racemic mixture is optically inactive due to external compensation. Both isomers rotates the light, but they compensate each other. One rotate to the right, then other rotate by the same amount to the left. That's why net rotation is 0 due to external compensation. So Mezzo compounds as well as racemic mixture, both are optically inactive. So you see here that though this molecule has chiral center, chiral carbons, but even then this molecule is optically inactive. That means chiral carbon neither necessary nor essential for optical activity. So necessary and sufficient condition for optical activity is dissymmetry. We can say another example in which there is no chiral center, even then molecule is optically active. Let us discuss those examples. First is allenes. Allenes have cumulative double bond and the substitution on both sides should be proper. This carbon, terminal carbon, should be attached to two different atoms or groups. So allenes are found to be optically active if terminal carbons are attached to two different atoms or groups. So allene is optically active though there is no chiral carbon. Second example is alkylidenes. What are alkylidenes? A, B, A, B or Ba. Again optically active. Spirons. Two atoms attached should be different on both sides. So this is spiron. This is also optically active. And last example is biphenyls. Two rings attached by single bond and both the rings are substituted unsymmetrically, and at least one group should be there at the ortho position, and that should be larger in size. For example, COH, biphenyl like this. It should have two rings attached by single bond and there is ortho substitution. Molecule should be substituted at ortho position and the substituent attached should be large in size. If we have a molecule like this molecule has plane of symmetry. As this molecule has plane of symmetry, it is optically inactive. So condition is there are two rings attached by single bond, but there should be ortho substitution first thing, and groups attached at ortho position should be large in size so that rotation is restricted. Let us recap the concept in which molecule has no chiral center, even then they are optically active. For example, this is allene. Another example is one of the double bond is substituted by ring in the allene, or both the double bonds are substituted by rings. And last one is biphenyls. So we see that molecule having chiral carbon may be optically active, but it is not always true. Even we see the examples in which molecule has chiral center and it is optically inactive. The molecules allene, alkylidenes, spirons with suitable substitution, they are optically active, but there is no chiral center. So molecules are optically active if it is dissymmetric. Dissymmetry is necessary and essential condition for the molecule to be optically active. Presence of chiral carbon is neither necessary nor essential for optical activity.